easy. You're just shifting stuff around. That's all we're doing.
You could give us the exam on time and just also give us the answer key at the same time. That way you know where to look.
I can give you guys multiple answer keys. So you have to find out which one is the actual.
Oh, that's just not right.
That could be an interesting exercise all by itself. It's like Indiana Jones, right? And the Holy Grail. He got to it, and then there are several cups, right? You just have to choose wisely.
And run away from the boulder.
Yep, stay away from the boulders. But that's the easy part. That's just the opening scene, right? All right. So let's go ahead and get started. We have new homework assignments. So as usual, I will show you your new homework assignment before we start to talk about the topics. This is your new homework assignment. Create a folder called Add Flags in your home folder and use that folder to contain all the programs. In other words, this time you will have multiple programs. Each program should use the following template. Now every time you see the angle brackets surrounding something, that tells you it is it is a token to be replaced by something else. So this part here has to be replaced by some kind of pattern. I'll explain that later. And this part here has to be expanded into some sort of explanation, which I'll also explain. The rest of the program is fairly simple. I think I forgot one thing. It's not a big deal. It's just that it's not entirely right the way it is, because I forgot to say dot text first. You don't have to do it. It's just a good habit to do it. So I'll just go ahead and update it right away. Okay, so here's your program. Dot text, we switch to the code section, and then we declare underscore start to be a global symbol, which means it has to be exported to the linker. And underscore start is here. That's the beginning of your entire program. So this is the kind of stuff that you have seen over and over again. We start with a no op instruction, just in case someone wants to stop at the very first instruction. There are only two instructions that are important. The first instruction is move L, $, and then the question mark, which is something that you have to replace, to EAX. The second instruction is add L, $, and then another question mark, EAX. So your job is to replace the question marks with something, so that by the time I get to checkpoint, in other words, if I stop at this instruction, when I stop at this instruction, I want to have a particular flag combination. We haven't talked about a lot of the flags yet. We have only talked about 2 of the 4 flags so far. We talked about the carry flag, which is the carry bit that got rolled off of the number that we could not store in the destination. We also talked about the 0 flag, which becomes 1 if and only if the result itself is 0. So we talked about those 2 flags. There are these bunch of flags, okay? So you have to give me 16 programs, because there are 16 combinations. Remember, there are 4 individual flags. Assuming the flags are independent, you have 16 possible combinations. Does that make sense? Yep.
You said we went over the 0 flags, and what was the other name of the other flag?
We went over the carry flag. We also went over the 0 flag. Those are the 2 flags that we have talked about so far already. In other words, I want you to give me 16 files. The first file, XXXX, simply means all 4 flags have to be clear. They all have to be zeros. The next one is XXXS, which means the first 3 flags are zeros. Only the sign flag, which we will talk about today, needs to be a 1, and so on. Okay? Now, it looks like it's a really nasty combination, 16 programs to write. But some of these are related. Okay? Some of the flags are not truly independent. So you will probably figure out, some of these combinations is just trivial. It is not possible. If one of these combinations is not possible, then you have to come up with an explanation and tell me why it is not possible. Yep.
Can I ask a question about one of them that may not be possible?
Well, it'll become obvious. Okay, it will become obvious why some of these combinations cannot be possible. Yep.
So do you have to replace the question marks with certain things?
If the combination is possible, you replace the question mark with actual values, so that by the time we get to checkpoint, the flags, that particular flag combination will be true, or you will end up with that particular flag combination. So you have 16 programs to turn in, and here we have CXOX, which basically means the carry flag has to be a 1, the Z flag has to be a 0, which is the second position, the O flag has to be a 1, that's the third position, and the sign flag, which is the last one, has to be a 0. Does everybody understand, how the combination works? Not the meaning of the flags, just how I come up with the 16 combinations. Okay? So for a specific pattern, okay, let's say we deal with CXOX here, then you have to create a file with exactly the same name, cxox.s. The case has to be sensitive, okay, because Linux file systems are case sensitive. The objective is so that you can turn in your program and my script can do it, can grade it automatically. Okay, it is entirely possible, except for the explanation part. I actually have to read it and see whether it makes sense or not. Yep.
Do we actually name the files XXXX?
Yes.
Okay.
Mm-hmm. And once again, it is case sensitive, so you have to use lowercase x to mean that flag is 0. Any other questions so far? No questions so far. Your only degree of freedom is to replace the question marks with specific constants. That's the only thing you can do. And after you're done, you have to use the tar command here to create the usual tarball thing, and then turn it in. Okay. Any questions so far? Yep.
So replacing question marks and then you're writing, you said 16 different programs for those patterns?
Yep. Each one is one file. If it is possible, you tell me how to make it happen. If it is not possible, you use the explanation to explain to me why it is not possible. The explanation cannot be, it is just not possible, or I cannot find a case, to make it happen. Okay, so the explanation has to be more complete, and I'll talk about that a little bit later too. Okay, are we doing okay so far? Yes?
So this is exactly the way it's supposed to look like?
What it looks like? The program, or are you talking?
The answer, like the X.
That's not the answer. That's the name of a file that would create that particular flag combination. Okay?
So the program going to print that way out?
Sorry?
Is the program going to print out the
No, the program does not print anything. I will also show you guys how to check the flags later on. Okay? But the first thing is I cannot talk about this. I have to talk about the program that is due today. And that one is kind of interesting. So let me just go ahead and do that homework first, and then we'll come back and talk about the flags after an addition. So this is the mixed up homework. I'll do exactly the same thing as you will have to do. And I could have used the GUI program to open it up, but I'll just go ahead and use the command line to do it. Okay. And I have to change to today's folder. And I have to go find the program. Where is it located? It is operands. Okay. So now I have, I didn't put it into my home folder. I put it into today's folder. So this way you can download the zip file that I create at the end of today's class, and you can also look at the solution that I have. I will try to annotate the program as much as I can inside a file, so that way you don't have to listen to me and read the file at the same time. You can just read the file, and hopefully it will self-explain all the things that I need to explain. So we have operands here, and here we have our program. I'll go ahead and just use VI to look at the program and turn on syntax highlighting. That just kind of makes things a little bit easier to read. Okay. The first thing you have to think about is, Okay, let me just go back to here. We want EDX to have this value at checkpoint 1. Okay, so can someone tell me what if the program crashes before checkpoint 1?
Then it won't have that value.
Then it does not fulfill this requirement, right? So that means any program that crashes before checkpoint 1 will not get full credit, if any credit. Okay, I might change my mind and give some partial credit, but it definitely won't get full credit. Okay, now of this entire pattern here, which is in EDX, which part can only be specified by EDX? The most significant 16 bits. In terms of the hexadecimal number, what are those digits?
The first 4 digits.
The leftmost 4 digits. Okay, the leftmost 4 digits would be these 4 digits. So that means when I get to the program, the most important part about this instruction is this is my only chance to get 4000 into the most significant 16 bits of EDX. The rest I can mess with it later because I have other instructions like the next one to deal with the least significant 16 bits, and I have yet another one to deal with the least significant 8 bits. So I can worry about that later because those bits will be overwritten anyway later on. Okay, so knowing that I need to have this pattern here, what is the byte sequence that I'm looking for? I'm looking for the byte sequence of 0040 because 00 in this case is the less significant byte and 40 is the more significant byte. Okay, so I need to go find that particular pattern within the data section. Now you don't really have to make a map out of this whole thing to see it because you can use the debugger to help you out. Okay, the debugger is a great tool to quote-unquote cheat in this case because once you know what byte sequence you're looking for, the debugger can list everything. It can handle the rest. So do you guys want to see how to use the debugger for this purpose?
Yes.
Okay. Of course, it's all getting recorded, right? So that's good. That means I can ask questions of about the same difficulty level in the exam.
Can we not show this one?
Okay, so what I would do is I would go back to the program and just comment out these particular lines because otherwise the assembler won't be happy and it won't even assemble. Mixed up. Mixed up. Yes. Okay, GDB mixed up. Okay, so I'm now running the program. I don't even want to run the program. There's no need to run the program because my objective is just to dump the data section, just to see what is in the data section. Because I'm looking for what sequence again? 0040. Okay, so that's the most important part. I can't even remember how many bytes there are. Can anyone remember that?
I think it's 28.
I can find that out if I just do an object dump. Dash lowercase t mixed.
Or you just press L and look at it.
There's a way to shout out. Cannot remember how to do it. Nope. Okay, there we go. So I just need to spell out as shell. Not a dynamic object.
If you had typed L and just looked at it by now, we'd have had it done.
Yeah, but I was hoping that I can just use you can use object dump because it will actually give me the size of each section, and that will just give me the count, the number of bytes that I need to dump. Because in this case, I would have to say it's L3 plus 4. L3 plus 4 is the last address in the data section. Does it make sense? Because here we have L3, this is L3 plus 1 plus 2, this is L3 plus 0 plus 1, this is L3 plus 2 plus 3. So L3 plus 4 would be the next available instruction that I'm not even using in this program.
Actually, you have a
What
dot
about the
dot
fill
in
got more.
and the int?
Hmm?
The
It's
fill
not
and
film
the int.
dot in right below there.
Oh, that's okay, I can handle that. Okay, because what I can do is I can print the number of bytes. I can print it like this. I can say, now remember, everything has to be typecasted as char pointers because otherwise they're natively int pointers, so the arithmetics won't be right. So here we have a char pointer casted by L3, and I can do subtraction now. And here's L1, but I have to remember the plus 4 after that, so we have 20 bytes to dump. Is that making any sense? Because I look at L3 here, I look at L1 here. L3 minus L1 as char pointers will give me all the bytes that I define, from here up to here. But I have 4 additional bytes after that, that's why I need to add 4. Is that making any sense? Yep.
What about the dot fill and dot in?
The dot, oh, you mean here? Oh, sorry about that, I missed that.
That's what we were asking.
We don't know
Okay.
anyway.
So that's plus 4, and these will be 2 bytes, and that will be 4 bytes. So that's it. So 26 bytes to dump. Okay, so let's go ahead and dump the 26 bytes that we have. 26 bytes. What format do I want to use? Do I want to use decimal? Hexadecimal makes the most sense, right? Okay. And I will start with L1. And here we have a memory dump of the 26 bytes that are important to me. And I'm just scanning this to find 0040. The first time that happens is here, and that's also the only time it happens. So the answer is unique, at least for the first part. Yep.
I noticed you're looking for 0040, and why are you looking for that? Because I know you put the last or the first 4 digits with them.
Okay. It has to do with the little endian convention or the little endian standard, because of the 16-bit patterns 4000. That is, I cannot store the 16 bits in 1 byte, right? 16 bits needs 2 bytes. But since the processor is only byte addressable, now I have to determine which byte goes first. Little endian says the least significant byte goes first or has a lower address. And that's why 00 has a lower address and 40 has a higher address. And that's why I'm looking for 0040, because when you dump memory content using the X command, the one that goes first on the left-hand side is the one that has a lower address.
So the 40 went first on the left-hand side, so it has a lower address?
Sorry, say that again?
So 40 went first, therefore it has a lower address?
No, 40 has a higher address.
Oh, okay. Oh, 00 has a lower address, so you put it goes first, the order?
Because when you list, it goes from left to right. Whatever is on the left has a lower address than whatever is on the right.
Oh, okay.
Okay. All right, so the next question is, what is this? What exactly is this? Well, we know this is L3. L3 refers to this byte here. This is L3 plus 1. This is L3 plus 2. L3 plus 1 is the start address of what I want. Okay? But I also have to remember the instruction is not a move W instruction. I cannot just move to the most significant 16 bits of EDX. Whenever I use EDX, I have to start from the beginning. Is that right? So that means when I use move byte, I have to roll all the way back and start with this byte here. Is that making any sense? I want this byte, this byte, this byte, and also this byte. But particularly, I want these 2 bytes to go into the most significant 16 bits of EDX. But since the move instruction is a 32-bit operation, I have no choice but to start with this byte here, which is L3 minus 1. Okay, so now that we know something, let's go ahead and I'll just use another window to do the editing. Okay, so we go edit mixedup.s. turn on syntax highlighting. And what I would do is I'm not coming up with a solution just yet. I'll just comment on this line here. I will say the effective address of the first operand is L3 minus 1. Is that making any sense? Now, the next question is, I haven't studied yet, so I don't know what this means, but yet I still want to verify L3 minus 1 is the right effective address. Can I do that? Can I check? Yeah, I can just change the program a little bit, remember to change it back to what it was, and use a direct operand. Because I can just use a direct operand, which is L3 minus 1, put a breakpoint right after this, and double check to make sure that if I use an effective address of L3 minus 1, it will give me the result that I need. Okay, so let me just kind of show you what I mean by doing that. Okay, so I will say fix later, okay, restore later, because otherwise I would forget. So instead of this instruction, I would say move, let's see, L3 minus 1 to EDX, just like that. In fact, that instruction doesn't even have to be here. It can be all the way up there. Because if you look at move L3 minus 1% EDX, does it depend on the initialization of anything else? No. Nope, does not depend on anything else. So I can put it right at the beginning, because I just want to check to make sure that this effective address is correct. Okay. So go ahead and save the program and get out of the debugger. Reassemble, relink, and re-GDB. Go into the program again. This time we want to put a breakpoint on the no-op instruction, because I cannot put a breakpoint on the very first instruction. So we say B27, run the program, take a look at EDX. Excellent. This is exactly the pattern that we want.
So we're done, right?
Okay. So that means, well, that's why I talked about, if your program crashes before it gets to checkpoint 1, then it does not count. Because the instruction says very specifically, when I stop at checkpoint 1, this has to be the value. So if a program cannot even get to checkpoint 1, it does not count. Okay?
Just leave the comments and it'll work fine.
Okay. All right. But it's a good thing, because now I can at least verify that this is the effective address. The next question, okay, let me just go back here and restore the instruction as soon as I remember. So the next thing you have to do is to say, how can I make this operand to have an effective address of L3 minus 1? Right?
We're already subtracting 1 from it.
Well, the effective address of this particular based addressing mode is the summation of whatever is before the parentheses and the value of the register at the time this instruction executes. So since we have a -1 or -1 here already, that means EAX only needs to have L3 in it, because then it becomes -1 plus L3, which is the same as L3 minus 1. Now, can I check that? Can I see whether that is right or not? In other words, I'm working my way backwards. Okay, I look at what I need. I say, okay, I need L3 minus 1 to be my effective address. Check that first. Everything works. Now I work my way back just one step. Okay, because I can do something like this, can't I? Not in the form to be submitted. Okay, to be removed, just so that I remember that I have to remove it. And this one here, I have to say to be restored, because otherwise the program won't work. Okay, does everybody see what I'm trying to do here? I'm just trying to double check every step along the way. I'm not jumping multiple steps. I'm only doing it one step at a time. Okay. So now I go to the other tab here. Make sure I save the file first. Reassemble, relink, and run the program again. And this time I put a breakpoint on, okay, let's see, where is it? It's on line 31. Okay. Run the program. this single step will put L3 into EAX. I can always double check and see whether it makes sense or not. Seems fine to me, because if I say print ampersand L3, it gives me exactly the same value. So I know EAX has the right value at this point. I single step one more time, which is to execute line 32 at this point. I take a look at EDX. Everything is still good. In other words, I'm not really jumping steps. I'm just working out this program one step at a time. Okay. So once again, I get out of the program. I go back to the source code. I restore everything that I have to restore. I remove everything that I have to remove to restore the program back to what it was. I don't want to have to deal with EBX at this point, because nothing that I need to worry about has to use EBX at this point, so I just skip that instruction. So the next thing I have to ask is, how can I use this instruction here and say, how can EAX end up with L3? That's the question. Well, I cannot change the operand. In other words, I cannot change the first operand of this line to $L3 because I can only specify the question marks. So now the question is there anywhere in data space that has the pattern that I need?
Yeah, the first byte after L2.
Exactly. Okay, at label L2, I define 4 bytes, and those 4 bytes just so happens to be L3 itself. Okay, so now the question is, how can I make this work? Well, I have a suspicion that if I just go to L2 as my effective address, take the 4 bytes over there and put it into EAX, EAX should end up with L3. But that's just a suspicion. So to confirm my suspicion is right, I can just change the program. Okay, once again say restore, and instead of guessing my program and if you try to work from the beginning and you make one mistake and your program does not work, it's really hard to figure out where it makes the mistake. Okay, but if you work backwards like this, one step at a time, it has to be the very last step that is erroneous. So in this case, I can just say, okay, let's just cheat a little bit here. Okay, and I just intentionally say go to L2 and move whatever is in L2 to EAX.
You need a percent.
Oh, percent. But let's see what happens when I do it like this, because one of your questions in the exam is going to be, spot problems with a program. You will have to spot like problems like this, which means that your exam is going to be done online in the lab. You will have your debugger, you'll have your assembler, you have your linker, you'll have Google, you'll have Moodle to help you. It's open book, open notes.
And it still won't be enough.
Hmm?
And it still won't be enough.
Oh, I wouldn't say that. So I just changed my program a little bit here to confirm my suspicion, okay? And can everybody see, what is the approach here? I just work it one step at a time. So this will work, okay? I know for sure it will work. So that means, I want, okay, so I will take this out, restore the instruction here, because at this point I know the effective address of this has to be L2. How can I make an indirect operand to have an effective address of L2? Just make it L2, right? Just make it $L2. Initialize it to L2. So that's why I can go here and just change the question mark to L2 here. Are we doing okay so far? As far as the reasoning, the rationale, how I do it step by step. Now, I still have to understand all the addressing modes. I still have to know what they do, but as far as working my way back, this is the reasoning. You start with the anchoring instruction, which means this instruction, there's not much degree of freedom. I know this instruction has to do this. Start with that one, move backwards to see how I can make that instruction do what I need it to do. Okay. Now, once I have made this change here, it is a good idea to reassemble, relink, and just run the debugger again. I cannot run the entire program because I only have parts of it finished. So this time I can only finish it all the way up to line 32. I will have to stop at line 32. Okay, so run the program, look at EDX, and it still has the right value. But I am not at the breakpoint yet. Okay, so I know I cannot just say, okay, I'm all done, because I have to make sure the program can continue its execution. The first thing is it cannot crash. And then the second thing is, by the time I get to checkpoint 1, I still need this pattern to be in the register. Yep.
What if it crashes after checkpoint?
Sorry?
What if it crashes after checkpoint?
If it crashes after checkpoint 1, I don't think you can make it crash after checkpoint 1 and not before. Okay, so we'll go ahead and quit the program again. And then we go back here. Okay, we have solved the first mystery. Okay, we know how to get the most significant 16 bits into EDX. But we have 2 other instructions to worry about. Okay, so we'll go ahead and restore. We have this instruction here, and also this instruction here. And both of these instructions will use EBX for something. So now the question is, how can I define the value of EBX only once, but make sure that none of these 2 will mess it up? That's the question. Okay, with DX, which byte can I change in DX that I will not overwrite when I overwrite DL? DH, right? The most significant 8 bits of DX cannot be changed when I overwrite DL. So I got to make sure that I put a 2-3 into DH in this instruction, and this one has to put a 2-3 into DL. Okay? But I have a lot of choices in that case. So let's go ahead and take a look at all the 2-3s. I have a whole bunch of 2-3s, including the dot fill. The dot fill has a bunch of 2-3s. There are 2 2-3s here. And then I have 1 2-3 and also this 2-3 here. So these 2-3 are also consecutive.
You have 2 more above that, above L2.
Yep, I have 2 more, but those 2 are not consecutive. They're not right next to each other. They don't have to be right next to each other, but the math has to work out. Okay? All right. So we look at this instruction here, and then we say the effective address of this is L2 plus EBX times 2. Oops, times 4, right? And what about the next line here? Do we know the equation of the effective address? This is the effective address of, do we know what is EAX? EAX is L3, okay? So this is L3 plus EBX, EBX times 2.
Plus something.
Plus whatever the question mark is. Okay, EBX is an unknown, so we'll call this X, and we'll call that Y. We have 2 unknowns. But how many choices do we have? Really?
You got rid of the comment on the front of that line.
Sorry?
You got rid of the comment on the front of that line.
Get rid of the comments. Yes, I did.
Just making sure.
Yeah, because I'm just going to solve this equation altogether. Okay, so that means I have to solve this part as well. Okay, what do I need to move into EBX to make this happen? Now, typically, now at this point, most people can just, sequentially test different values. If you don't mind spending the time, it has to be somewhere within the range of the program, right? And because we are multiplying x by 4, how many choices have you got? Okay, this is L2. L2 is right here already. So this is L2, this is x being 1. And so here's 1, 2, 3, 4. This is x being 2. Okay, so 1, 2, 3, 4. And this is x being 3. Okay, so you don't really have a lot of choices right here. You only have 4 choices. Which one do you think makes sense? Okay, we'll try. Okay, we know 0 doesn't make any sense. Why do we know that 0 does not make any sense? It is an address. But sometimes it may just so happen to have 2, 3, but that's not guaranteed, right? So that means, we can start with, x being 1. Now, if x is 1, does it make sense? Okay, let's take a look. This is L2 plus 0. L2 plus 0 refers to the first byte of the dot int. L2 plus 4, which means x is 1, is referring to this byte here. Attack, this is 4, 0. This is not 2, 3. But remember, we need to make sure the more significant byte of dx is 2, 3. Right? Because we are now trying to fix this particular part. And in this case, 4, 0 is the least significant byte, which specifies DL. We are going to overwrite DL anyway. Okay, so it's perfectly fine if DL does not end up with the value that we want. But this being a higher byte or a byte with the next address is going into DH, and that's what we want. So this definitely will work out. So let's say that, so what I'll do is I'll say x being 1 works out of this instruction. The next question is, will it also work out for the next instruction? Can I use x being 1 to fix y? The answer is yes, right? I don't really care what x is. If I fix x, I can always adjust y to make it work. That's the easy part. Because y specifies a byte addressable part. It does not have a constraint of being always have to multiply by 2 or multiply by 4. So my real worry is really just x. Once I know what x is, I can always readjust to find out what y has to be. Okay. Okay, so if x is 1, that means the effective address is becoming, so this is an effective address of L3 plus 2 plus y. Okay, so where's L3 plus 2? This is L3. This is L3 plus 0 plus 1. This is L3 plus 2. So what do you think y can be? There are tons of choices here. Just pick one.
Plus 1.
Negative 1 will work. Plus 2 will also work. Okay. I mean, you guys can also do the calculation to go all the way back to this 2, 3. That will work too. I mean, you just pick any one of the 2, 3s and it will work. Okay, but the closest one I can pick is the one right next to it, which is just negative 1. Yep.
Oh, so how are you figuring out those number guesses right now?
Which numbers?
The negative ones and the.
Okay.
I got you all the way up to that, and I'm trying to figure out.
Okay, do you remember how I figure out x can be 1? Because I want this 2, 3. There are choices. There are tons of choices here. You don't have to do it this way. I mean, there's another 2, 3 here. Now, but the problem is, whatever address I pick here, this effective address has to be L2 plus 4 times x. So there are only certain locations that will fit into that part here. So because it's more of a constraint, we have to work this one out first. Okay, and x being 1 just so happens to work out.
Oh, so you just basically just picked one randomly and just happen to work out the equation?
Well, you don't want anything above 4.
Well, you can try out all the possible values. There are only so many possible values that we can try. Because, okay, this is L2, right? L2 is right here. Now, L2 itself is pointing to the least, L2 itself is the address of the least significant byte of an address. So those 4 bytes, I don't know what they're going to be, so I cannot rely on those 4 bytes for sure. You can actually work your way back. Okay, what is L2 minus 4? Which byte are we referring to? L2 minus 4. It's a 4, 0. It's not a 2, 3. Do we have any bytes before this? The answer is no. Because the other 4 bytes before this is also another address, so we know we cannot rely on that. So we know x cannot be negative 1, it cannot be negative 2. We also know it cannot be 0 because if it were 0, it will be referring to a part of an address. If it is 1, it just so happens to work out just fine because we'll be referring to this 2-3, and that will load into DH of DX.
Okay, now how are you counting bytes? Because I think that's mixing me up. Because when you say 0, then you point to something. Then you say 1 and you point to something. Are you counting each single number as 2 bytes or each?
Okay. This is L2 dot int. How many bytes do we have in one dot int?
2.
4.
Oh, 4.
Well, that's why you cannot count because you have to know how many bytes there are in each construct. A dot int has 4 bytes, so that means L2 plus 4 is going to refer to this byte here. But since it's a move word instruction, we are not just moving this byte here, we are moving both of these bytes. And because the 2-3 has a higher address, it will be loaded into DH instead of DL. So that works, that works exactly the way we want it because we want DH to have 2-3. We don't care about DL because we are going to overwrite DL anyway. Does that make any sense?
Yeah, so each word, depending on if it's an int or the different type of words, they carry different type of values. That I didn't know about that. Was that so how much would L3 carry?
L3.
Yeah, the word L3.
Dot word.
A dot word is 2 bytes.
Oh, okay. So only those are the dot words.
Yep.
Word, dot fill, dot
And those are the things that we have talked about, some times ago. So you might want to review the notes, just to make sure you understand what those things will do in your program. Okay. So the way it works out right now is we know EBX can be a 1, but if that is a 1, we need this one to be a negative 1. I mean, among other choices, this will work out. There are lots and lots of choices too.
Why have to be -1?
Sorry?
Say why have to be -1?
It doesn't have to be.
It doesn't have to be -1, but -1 is the closest one that works out. And I think this one doesn't have to be a 1 either. I think a 2 would also work because this is 1 byte. If you count 1, 2, 3, 4, this is also a 2-3. So there are quite a few choices.
How about -1 for x?
What?
-1 for x.
-1 for x is not going to work
Which is short.
because we'll be going to L2 minus 4. L2 minus 4 is going to refer to the least significant byte of this one, which is... Oh, it will work out too. Yep, sorry, I was wrong. So x being -1 will also work out. So there are many solutions. As long as the solution works, it's good. Do you guys prefer when there are multiple solutions, or do you prefer when there's only one solution?
Depends.
There can only be one. No, I think in this case it makes it easier because there are so many places where you can find the pattern. The most difficult part, I think, is just to understand the addressing modes, because once you can think in terms of effective addresses, and once you understand the little endian versus the big endian difference, and once you know how memory locations are populated by dot word, dot byte, and dot int, the rest is really just as exercising your reasoning and go like, okay, this makes sense, and then move on to the next one, and so on. Any questions about this particular assignment, or the solution of it? No questions? If there are no questions, I will save this version, and just to make sure that it works, I will go ahead and do this one last time. This time I will put a breakpoint on checkpoint 1, run the program, and then check EDX at that point. Oops. Ooh, it's not right. Okay, so let's see here. L3 plus 2. This is L3. This is L3 plus 0 plus 1. This is L3 plus 2. I have to minus 2 because minus 1 will get to the most significant byte of the 0x23, which has a leading 0, 0 that I did not write here. So a negative 2 will work. Yeah. Yep, double check, make sure.
Was this an example of why you check your work before you turn it in?
Yes. All right, everything is good. It does not crash before checkpoint 1 either.
Step forward.
Try
stepping forward.
Sure. Run again. Single step. Or just continue. Program exited normally.
I'm just not trusting you.
That's good. That is good. Inquisitive minds can be useful in many situations. Okay. Any questions about addressing modes at this point? Operands, addressing modes, that sort of thing? Yep.
When do we get to actually do something that will invoke thought with keys?
We'll get to it. We'll get to it. This class will accelerate, as time goes on. So, the pace will only pick up. It will go faster in a little bit. All right. So now we can move on, and we're getting back to the adding module. And last time we talked about the 0 flag already, and we have a question about what about signed numbers? Okay. How do we represent negative values? So let me ask you a question. The question is, let's say we're not dealing with a 32-bit architecture. Let's say I'm only dealing with a 4-bit architecture, just for easier calculations. Okay. With 4 bits, 0, 0, 0, 0 has to represent which value? It represents 0, right? I mean, it makes sense. 0, 0, 0, 1 in base 2 represents 1. 0, 0, 1, 0 in base 2 represents 2, and so on. So we work our way all the way up to 1, 1, 1, 1 in base 2, and it represents 15. Where's my negative 1? Well, it seems like we have a problem here. Because when we represent negative numbers in base 10 in normal calculation, how do you note a number, a constant, is negative? How? You put a negation sign before the number. In other words, if you want to say negative 5, this is how you write negative 5. But we don't have a negative symbol in binary, okay, because they're all zeros and ones. So the most intuitive way is to say, well, we'll just use 1 bit to represent the sign of the number. Well, it is actually some system used to use that, but it was not a very good system. Because for 1, you will have 2 zeros. Because you will have non-negative 0, and then you have negative 0. They represent exactly the same value. But you're using 1 binary bit pattern to represent something that is redundant, something that's already represented. So that's why in modern processors, we only use 2's complement to represent negative values. Okay. Now, negative values, there are ways to look at it. This is one way to look at things. But remember, with 4 bits, how many possible combinations can we have? We only have 16 combinations. Okay, if you count everything from 0, 0, 0, 0 up to 1, 1, 1, 1, we only have 16 distinct bit patterns. Instead of looking at this as a number line, look at it as a number circle. So now you have 0, 0, 0, 0 here, 0, 0, 0, 1, and 0, 0, 0, 2, all the way up to here, which is 1, 0, 0, 0. This is 1, 0, 0, 1, all the way up to here is 1, 1, 1, 1. Does it make sense? I'm just adding 1 as we go in a clockwise fashion. Okay, that makes sense. But it doesn't solve the problem of representing negative numbers. What about I can tell you this? What if I tell you this represents 1, makes sense. This represents 0, but if I go in this direction, I'll just be doing subtractions. 0 minus 1 is negative 1. Oh, okay. So that means I can use 1, 1, 1, 1 to represent -1. And the next one is 1, 1, 1, 0, which I can use to represent -2. And then we have -3 all the way up to here. This will represent -8. And then 0, 1, 1, 1 will represent 7. Now this is somewhat, okay, someone can say this is somewhat an arbitrary choice to see which one is, which bit pattern represents which number. Yes, go ahead.
7 or -7?
That is 7. That is regular 7. This is -7. Okay? So instead of looking at this as a number line, I'm now looking at it as a number circle. Okay? And there's a specific reason why it is a number circle. It's because we only have a limited number of bits. Now, yes, we have new processors that have 64-bit registers, but 64 bits nonetheless is limited. Okay? It is still a circle, except the circle is a whole lot bigger than this one, but the concept still applies. So the next question is, how come I choose this guy to represent -8 instead of 8? Because if you go from 7 to 8, it is 8. But if you go from -7 to here, it becomes -8. So why do I choose -8 to be the value represented by 1, 0, 0, 0? It's because the math just works out. Okay? It is a very, very ingenious way to represent negative numbers. The next question now is, how do we come up with these numbers? How do we know, okay, let's say, I want to represent -5. What is the value of -5? What is the bit pattern of -5? Well, what we do is we use a system called 2's complement. Okay? So let's take a look at 2's complement, which is on this slide. Okay. The slide is kind of, it looks complicated, but it's not. 2's complement is based on bitwise NOT, and bitwise NOT is also called 1's complement. Okay? Bitwise NOT is the tilde operator in C. Can everybody see what the tilde symbol is? It's the, the wavy thing on your keyboard. It's a shift backtick. Let me just, use where's my pen?
It's next to the one.
This is the tilde symbol. Does your C class talk about the tilde symbol?
No.
The bitwise NOT operator? Okay, that's okay. We don't need to know that from the C class. All we need to know is the bitwise NOT operator will turn a 0 into a 1 and a 1 into a 0. But it does not apply to the entire bit pattern. It applies to every single bit of a bit pattern. Okay, examples. Okay, so let's go ahead and take a look at, now the bitwise NOT is also called 1's complement, so I'll use C1 to refer to it. So if I want to find the 1's complement of the bit pattern, let's say 1, 0, 1, 1, I turn every 1 into a 0, I turn every 0 into a 1. So that will become what? Just like that. And I can do it to any bit pattern, okay? I can do it to 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, okay? The thing is, the output has to be the same width as the input, okay? If you're dealing with 8 bits, then you're always dealing with 8 bits. So in this case, the output is going to be 1, 0, 1, 1, 0, 1, 0, 1. So are we doing okay so far with bitwise NOT? Okay, so in C, what you can do is to use the tilde symbol and say the tilde symbol of 0x hexadecimal, let's say 5A, I chose one that is really easy, is a 0xA5. Because 5A is the bit pattern of 0101 1010. So when you take the negation of that, it becomes just the opposite, which is 1010 0101. Okay? Any questions at this point? Nope? Okay. So now we can define what is 2's complement. 2's complement of 1011 is 1's complement of the same thing, 1011, but you want to add 1 to it. So there's a little weird thing called adding 1 to the whole thing. Well, let's work it out and see if we can find it. Well, find out what is the 2's complement of 1011. What is the 1's complement of 1011, which is the bitwise knot? Okay, that's easy. 0100. This is something that we have done just a little bit earlier. What is that pattern plus 1? 0101. Right? So are we doing okay so far with the definition of what is 2's complement and what is 1's complement? Okay. So now I claim, tag claims that 0101 can be interpreted as 1011's arithmetic. How do you spell arithmetic? M-E-T-I-C, arithmetic negation. Okay. I don't even care what value they're representing. I'm just saying that they are each other's arithmetic negation. Yep.
Okay, we are using 1, 1, 1, 1 to show -1 and 50, both of them. How do we just like tell it to
Well,
the assembler
that's
or
okay.
keep it
That's a very good question. That's a very good question. The question is, we can choose 1, 1, 1, 1 to be 15, and yet on that picture, I choose -1 as the value that it represents. The bottom line is, your program chooses how you want to interpret the pattern. Okay? In other words, you can look at a particular bit pattern, let's say 40 in hexadecimal. Okay? Now 40 can represent a particular number, but it can also be interpreted as an ASCII value. So it is entirely up to your program, the instructions, to treat the bit pattern in a specific way.
So, but in C++, we have like variables to show that.
Sorry?
We have like variables. In C++, we have
Yes.
like ways to show that. How do we show
But
that?
in assembly language programming, you do not have types. So when you don't have types, then it makes no sense to talk about what is signed and what is unsigned. Now, I can give you guys a preview already, okay? This is like about a week or so down the line. In assembly language programming, it is not in the declaration that you specify whether something is signed or not. It is when you interpret the flags after calculations that determines whether you want to treat the bit pattern as a signed number or an unsigned number. Okay? So I know it doesn't make any sense at this point, but in C, it is with a data type. In assembly language programming, it is up to the instructions, especially conditional branch instructions, that determines how you want to interpret a bit pattern. Okay, so it's up to the instructions, not the data type, because we don't have data types when it comes to assembly language programming. Okay, but regardless, let's take a look at this particular claim here. What do you think is a property of a number and its arithmetic negation? What happens when you add them together? They should go back to 0, right? Well, let's go ahead and check. So now we have, okay, so the sum of these 2-bit patterns should be 0. Okay, let's check. Someone will say, but check, I know it's not going to work out. Well, let me show you how it works out. 1011 plus its 2's complement, which is 0101. This is also a good chance to practice our bitwise addition. I use one row to represent the carry because when I use a text editor to represent stuff, it's a whole lot easier to do it this way. Okay, what is 1 plus 1?
0 with 1 carry.
0 with a carry. What is 0 plus 0?
0.
0, okay. 1 plus 0?
1.
1. What is 1 plus 1?
0.
0 with a carry. 0 plus 1?
1.
1 plus 1
0.
with a carry. That's a 1. That's a 0 with a carry. I just proved myself right. But tag, there's one additional carry. Remember what I said? The width of the output has to be the same as the width of the input. Okay? If I only have operands that can specify 4 bits for my input, I can assume the output can only store 4 bits. So that works out. this additional carry cannot be stored in the destination. It's just floating around as the carry flag in the calculation. Okay? So it works out. Okay, great. So that means if I look at these as values, they should work out as well, right? So this means if we interpret 0101 as 5 in base 10, then 1011 as a 4-bit signed number represents -5. It just works out that way. Okay? Did I change my rule for addition so I can account for signed addition? No. It's exactly the same way that we added as of Tuesday. Remember we talked about binary addition on Tuesday? We use exactly the same rules. It works out just fine. Yep.
How about if we have a subtraction? Are we gonna get, for example, 5 minus 5, which is
Subtraction works out as well.
okay, it's the same.
Yep, subtraction is going to work out. Okay, so let's go ahead and try some values just to confirm that this is a reasonable representation of negative values. Yes?
If you try to choose complements of 1000, just go back to itself.
Yes, it does go back to itself, but 8 is out of the bound of a signed representation using 4 bits. In other words, if you use that circle, 8 cannot be represented as a 4-bit number, as a 4-bit signed number. Okay, that's a good question. Okay, so let's go ahead and try something here. Let's go for 85. Okay, what is the bit pattern of 85? Well, I'll just go ahead and cheat and use my calculator. Well, now that we know how to do it, we can use a calculator. So we have 85, and we want to turn it into a binary number. Binary, where's the binary?
You got the programming.
There we go. We just punch the enter key. Okay, so this is a 01, oops.
Oh,
Right. Okay, 85.
It's dash is easy.
Hmm?
It's easy.
01010101. Okay.
Can't miss it.
Okay. And okay, I'll pick another one that's easy. 32 is what? 000. Oops, I think it's one too many.
Yeah, and then 4 zeros.
Yep, that's right. Okay, because this is 1, 2, 4, 8, 16, 32. Okay. Okay, so let's look at these two numbers. I want to calculate what is 85 minus 32. Okay, that's what I want to calculate. So this is the same as 85 plus the negation of 32, right? So that means if I take the negation or the 2's complement of this bit pattern here and just add it to this bit pattern, I should end up with the same result, okay? And the result in decimal is what? Is 53. Okay, so we want to double check and see if it works out. The 2's complement of 001, 00, 000 is easy. What is it?
110.
Okay, it's this 1's complement. Okay, we'll work it out one step at a time. Plus 1. So that would be 1101, 1111, plus 1. And these are all binary numbers. And that would become what? 111, like that. Right? Okay, base 2 number. So now I have to do the addition. So now I say 0101, 0101, plus 111, 00000 is the following. Okay, we leave one row for the intermediate sum, and then we use another row for the carry, and then we use the final row for the actual sum. 1 plus 0 is 1. 1 plus 0 is 1 with no carry. 0 plus 0 is 0. 0 plus 0 is 0 with no carry. 1 plus 0 is 1. 1 plus 0 is 1, no carry. 0 plus 0 is 0. 0 plus 0 is 0 with no carry. Okay. And that's a 1. And here we have a 0 with a carry. And the previous calculation has no carry, so that's a 0 as well. And this is a 1. 1 plus 1 is a 0 with a carry, but that last carry cannot be stored. So now the question is, does this actually represent the value of 53? Okay, this is 1 plus 4 plus 16 plus 32.
48, 52, 53.
Yep, it all works out. So this is a good way to double check, just to make sure, that the math makes sense. Okay, so let me just add here, which is 53, magically. Okay, so according to this way of encoding or assigning negative values to bit patterns, what is common to all negative values? They all have a most significant bit of 1. Can anyone guess how the sign flag is defined?
If the most significant bit of 1.
It's the most significant bit of the calculation. That's the sign flag. Yep.
So then, if I'm in C and I have something that's signed, and then I do a C out and say I cast it as an unsigned,
Yes.
is it going to read the bit pattern and just spit out a completely different number because of this?
It will spit it out using the unsigned interpretation.
So it's not just, if I had -8 and then I cast it as an unsigned, it wouldn't give me +8, it would give me
In a 4-bit system, it will give you exactly 8. But since you're probably using a 32-bit system, it will give you a much bigger number than -8. It will give you 2 to the power of 32 minus 8. That will be the number printed on the screen. Yep.
So, since we're dealing with 32-bit processors, the most significant bit is
Bit 31.
the one that is responsible for our sign. Does that mean that our sign is technically stored in the middle of our numbers somewhere on a little Indian system?
It is still the most significant bit. In terms of location, where you put it doesn't really matter.
But where is it physically stored on our little Indian 32-bit systems?
Okay. So your question is, when you look at memory locations, you have 4 bytes, right? So this is, let's say this is L1 plus 0, plus 1, plus 2, plus 3, okay? So these are the 4 bytes for a 32-bit number. If this number turns out to be a signed number, or you want to interpret it as a signed number, which one is the most significant byte? This one, right? So this becomes your signed bit. It's the most significant bit of the most significant byte.
So then our sign bit is basically thrown somewhere in the middle of the bit pattern.
No, it's not. It's the most significant bit.
Yeah, but the most significant bit of that byte happens to be 7 characters from one end and 24 characters from the other end of the integer.
What? I don't...
It's got 24 leading zeros, followed by that 1, and then 7 trailing zeros.
No. No, this is the most significant bit. When you write this out as a 32-bit number, this is bit 31, and this is bit 0. So when you write it out, then it's the same as moving this one over here, this one over here, and this one over here. The sign bit is not in the middle of anything. There is no positioning within a byte. Remember, we don't talk about bit position, left or right within a byte. When you look at this as an actual number, this byte goes into this position, this byte goes into this position, and this byte goes into a position behind the screen. But nonetheless, okay, it's still, you look at this entire thing as one 32-bit pattern. And this is the most significant bit, which is the one that is the leftmost when you look at it that way. Yep.
Hey, so when we did that subtraction, how does it know not to turn that lingering carry flag, that single bit, into a larger number?
Because you cannot store this one single bit here. This bit cannot be stored.
How does it know that it can't be stored, though?
Because this is an 8-bit system, right? So your registers are all 8 bits.
In this example, we're just pretending.
Exactly, but you can expand it to 32-bit if you want. I just don't want to write a whole bunch of zeros and ones on the screen to deal with a 32-bit system. But it's the same thing. If you have a 32-bit system, then the source will be 32-bit, but the destination is also 32-bit. So that one extra carry flag cannot be stored into the destination. It has its own little place called the carry flag to store it. Yep.
Maybe this is off topic, but in a 32-bit system, is there a way to do 8-bit math?
Say it again?
In a 32-bit system, is there a way to do 8-bit or 4-bit math?
8-bit or 4-bit math? Signed or unsigned? Well, addition itself is insensitive to signage. The only calculations that will depend on the signed versus unsigned interpretation would be multiplication and division. Subtraction and addition are sign insensitive. So the answer to your question is yes. The way you do it is you have to do a bitwise, you have to do a bit mask, on the calculation, or just do a bit mask, apply a bit mask at the final result, and that's all you have to do. Any other questions at this point about the signed interpretation, the whole concept of using 2's complement to take the arithmetic negation of a number? That's okay? Everything is cool? Okay. So now that we understand what is 2's complement, we can now talk about the last flag that we haven't talked about. We have talked about the carry flag, right? The carry flag is really just the last carry from a calculation that cannot be stored. The Z flag is easy. The Z flag simply means, if the Z flag is 1, the result of the calculation is a 0. We have just introduced the sign flag. The sign flag is the most significant bit after a calculation. And what is the missing flag? The O flag. Okay? The O flag represents overflow. Okay? Now, what does it mean when something overflows? It means the sign of the result does not make sense. Now let me say that again, because you will hear me say this at least 6 more times in the next week or so. When the overflow flag has a 1, it means the result of an addition does not make sense because the sign it does not make sense. Let me give you an example, and this is an example of addition. Now remember, whatever example I use in the class, you cannot use it in your homework. So the more examples I use, the harder it will to work on your homework assignment. Okay, so let's look at a 4-bit system, and we'll say let's add 1000 to 1000 as a 4-bit system. Okay, it's not hard. That's pretty easy stuff, right? But the question is now our focus is no longer the exact answer. Our focus is what is the sign of this addition? Does it make any sense? Okay, because you guys can work this out. This is so easy, right? Oops. Oh, that's right. Except there's a 1 here. Okay. That's our calculation. Does it make sense? No? Why not? Which part? The sign does not make sense, right? If you look at the first number, 1000, the most significant bit is a 1, which means this is a negative value. The second number also has the most significant bit being a 1, which means it is also a negative value. I don't care negative what. I just know it is a negative value. Okay, that's all I care. You go through the calculations using the same rules that we have used since day one, and you arrive to a conclusion of 0, 0, 0, 0. Once again, I don't even care about the value it is representing. I only want to take a look at the sign of the result. Negative value plus negative value becomes non-negative. The sign does not make sense. Is that okay? I can give you another example.
Can
Yep.
you apply example in the program so we should have an idea how to start the homework questions? Like how do we apply it in our program?
How do you
The
apply it in your
flags,
program?
yeah.
How do you know the flags?
Yeah. In the
Yes,
program.
I'll do that too. But let me just go through this one other example. Okay, this is just an extreme example. Let's take a look at this one here. Okay, it's not that hard. Now remember, I don't really care about the actual value. I'm just checking the sign of the result, because I'm just checking whether the sign itself make any sense or not. Okay. This one I don't have to work sequentially because I know the answer already. Okay? And the carry flag is a 0. The final carry is a 0. But I don't care about the carry flag. I care about the sign of the input and the sign of the output. Does it make sense? The input, this is a non-negative number. This is a non-negative number. The result is negative. I don't care negative what. It just does not make sense. So once again, the overflow flag will be set in this case. Okay, yep.
How does it know whether you've overflowed or not if you're doing a negative and a positive?
Sorry?
If you're doing both a negative and a positive, how does it know whether or not you've overflown?
If these two are different signs, you cannot overflow. Because a positive number plus a negative number, the result can be positive or negative. So there's no way you can overflow if one is positive and the other one is negative as input into the addition. Yep, go ahead.
I'm trying to figure out the utility of this. If we were interpreting them as all positive numbers and ignoring the negative flag, that doesn't make much sense. But so can we use that as like that can't be a negative number or that can't be a positive?
That's a very good observation. The observation is that's why I said what I said a little bit earlier. In assembly language programming, the so-called sign depends on the instruction, the instructions that you use to interpret the result of an addition. Okay, the addition itself is a sign insensitive. It is how you interpret the flags after the addition. Then it becomes meaningful. Because if you look at these numbers as assigned values, the overflow flag basically tells you, have you run out of the space that you can represent using that particular system. So that's why the overflow flag has a meaning. It is meaningful because if it is a 1, that means the previous calculation has just run out of values that you can represent using the width that you have chosen. Yep.
So I have a question. So since the sign of the result doesn't make sense, and we will have an overflow flag telling us that.
That's what the old flag does. Okay. The old flag is a 1 when the sign of an addition or subtraction does not make any sense. Okay. Now we haven't talked about the instructions that are actually going to read all these flags. All we know now is what does it mean when the old flag is a 0? What does it mean when it is a 1? There was another question there. Okay. Now that's okay. Very good. So there's one more thing to do because if you want to get started with your homework assignment, you will need this step here, because natively GDB does not give you the flags. So that makes it really hard to debug your program because you don't know what flag is being set and which one is right or not. So what you need to do is to use this link here. This is a link to a text file. Okay, you can click it, and it just brings you to a text file. Any time. Okay, so this is the text file. It is a GDB script file. It's just a regular text file. So what you want to do is to do this. I'm still recording, so if you cannot remember, it's okay. It is still being recorded. And I won't even use the keyboard shortcut. Right-click, copy. Okay? Because this way you can just watch the video clip. You don't have to listen to what I have to say. You switch back to the command prompt, which is the other one. And then what you do is you say cat2. Now this part is very specific. You have to name this file exactly the same as here. It has to be named GDB init. Okay? It has to be of this particular name. And then what you do is you just paste the content. So in this case, I can just go edit and paste. If you use putty, it's just a right click. Okay? And at the end of this, you type Control-D to end the cat file, to end the cat program. So now I have a text file. You won't see this file using ls. You have to use ls-a to see the quote-unquote hidden file. Any file that starts with a dot is called a hidden file in Unix. So this way I can confirm that I have a file called .gdb init. Now gdb init is a very useful file because I define additional commands that you can use in GDB. In other words, I'm expanding the number of commands that you can use by defining my own commands. For those of you who want shortcuts and stuff like that, you can also customize .gdb init to do whatever you want it to do. Okay, so now I'll just go ahead and run Mixed-Up itself. Remember to use GDB first. Now there are several things that are different. You can see there's a whole bunch of empty spaces here when GDB starts up, and it also confirms that I'm running TAC's own GDB initialization script. Okay, and I'm adding the commands. These are the commands that I'm adding. One is called flags, which is the one that you need for this assignment. So I can just run this program here, and put a breakpoint at checkpoint 1. Now obviously this program does not relate to your next homework assignment, but I'm just illustrating how to use the command flags. Okay, you have to run the program, and when the program has stopped, you just say your flags, and it will tell you which flags are turned on. I think the first one is CS. I cannot remember. I think it's CZSO. I think it's the same order as in the homework assignment. I can always double check on that. Okay, quit. CZSO, which is the same order, if I remember correctly, as the homework assignment.
What does the L denote?
Don't worry about the L. Okay, just kind of ignore the L for the homework assignment. The L actually stands for less than. Okay, but we don't want to take a look. We don't want to look at L as less than until we get to the point of comparison. Because right now we're only doing addition. We're not comparing numbers yet. Okay, so let me just double check that one last item before I let you guys go. So this is CZOS. Okay, I flipped the order of the O and the S. Yep.
I was stretching, sorry.
Okay.
Okay. In the spots where you have lowercase x's, do you care what the flag is, or do you want it off?
The X means the flag is off.
Okay.
Yep, it has to be off. Yep.
Does GDB init by default look in the current directory for?
Yes. GDB will look into the current folder for a file name called .gdb init. If it does not find it, everything is good. It just means that you don't have anything to run automatically. If it does find, sorry?
Is there a more global way?
You can do a symlink, you can do a symbolic link to a particular file. So you can have one single definition, and every folder just do a symlink to that one file. But I don't think there's a global way to do it. Go ahead.
Where's so you have C equals 1, Z equals 0, and O equals 1, and S?
That's CXOX, because C is a letter. That means it is a 1. But the next position refers to Z, and since it has an X, that means it is not on. Do you guys want to change this to like C uppercase means on and lowercase means off? I mean, I can change that too.
No.
Yes.
So how should we interpret what you did before?
Sorry?
When you run the program,
Yes.
before you had flag and then you had C and you had an L. How can you interpret that?
Because we are not adding here in this homework assignment or
Right, exactly.
Yes.
How
How to
Well-
interpret, how to understand that.
How to
To
understand.
assimilate that.
Okay, so you
Okay.
want to look at you want to look at a particular flag combination, and then you have to ask yourself, is it possible to have this flag combination? If it is, if you think it is, then you have to think of how to make the question marks, how to specify specific values for the question mark to make that happen.
We have to do it backwards, basically, figure out the.
Okay, let me give you one example. Okay, one example, which is something that we have just done. Okay, let's take a look at this example that we have just done here. Okay, we have done a few examples already. So in this case, the result, I don't even need flags. I don't need to run GDB, but I can tell already the Z flag is going to be a 0 because the result is non-zero, right? The sign flag is a 1 because the most significant bit of the result is a 1. The carry flag is a 0 because the last carry is a 0. And then we also know overflow is going to be a 1 because I'm adding two non-negative numbers and the result yet is negative. Okay? So you have to work this out in your head. I mean, you cannot use this example. I mean, this is x, OS, okay? But you cannot use exactly this example anymore because I have just used it. You cannot do the sign extension of this and use it, okay? Yep.
So in this case, each register has its own flag.
No, the registers do not have the flags. The registers are nothing more than the input to the calculations and also the output of the calculation. Okay? The flags are stored somewhere else. It is stored in a special status register, which has specific bits to represent these particular values. Yep.
So where is that result stored?
This result here,
Yeah, where would that be?
in the template that I give you, it is stored in EAX. In other words, after the calculation, EAX is the summation of these two. Okay, so even though I haven't talked about the add L instruction, it doesn't matter because the 2-bit patterns, one goes here, one goes here. And because addition is commutative, it doesn't matter which order you're adding, it still comes out the same way. The flags will still be set exactly the same way, regardless of the order. But these are 32-bit bit patterns. Okay, so you have to keep that in mind because I'm using 4-bit examples in the class. So even if you just convert, those examples, it won't work exactly unless you specify the equivalent decimal values. Then it will work. Okay. Any questions? So you can get it done in a week?
No.
A few days? Less than a week? Yes.
You can do another example of the patterns.
Well, we are running out of time today, so I cannot do any more examples in class. However, if you guys read the notes, I think there are examples in the notes.
No, which we cannot use.
Yes, but you can borrow. Yes.
So for these two question marks, do you want us to put it